So now we'll switch to the stereoisomers. Geometric isomers, you're familiar, of course, with, well, you're not really these days familiar so much with cis-trans, even though I've tried to get it across to you in the organic. But if we think about these two sets of molecules, first of all, here you've got a copper that is coordinated to, in this case, it's a glycine. Glycine is an amino acid. There's the CH2, there's the acid group, there's the amino group. It's the simplest amino acid that we use because the carbon's just got 2 hydrogens on it. But amino acids, by definition, are bidentate ligands. They have a nitrogen that can coordinate, they have an oxygen that can coordinate, and their structure is such that when it coordinates to the metal via both the nitrogen and the oxygen, you've got a nice 5-membered ring. So anyway, here we have this nice copper that's got 2 of these bidentate ligands coordinated to it, and you can, I hope, see the difference between them. In this first one, the 2 nitrogens are on the same side, the 2 oxygens are on the same side. Here the nitrogens are on opposite sides of the copper, here the oxygens are on opposite sides of the copper. Cis means same, trans means across. So cis and trans. And we can also see this with a very, very famous coordination compound. This platinum compound here, very simple, diamine dichloroplatinum 2. Its short name is cis-platinum. It's cis because you've got the chlorines on the same side. They're next to each other. The ammonias next to each other. Whereas you can have trans-platin, in which the chlorines are across from each other. The ammonias across from each other. Cisplatin, extremely common. Arguably the most important anti-cancer agent or chemotherapy agent. Trisplatinum, completely inactive, associated with killing cancer. Okay, cisplatinum, transplatinum, cis and trans here. Another type of geometric isomer can be seen not with the 4 coordinate that we saw in the previous slide, but with octahedral species. So for example, if we think about this tetraamine dichlorochromium 3, okay, we can have this structure here in which the 2 chlorines are next to each other, or this structure here in which the chlorines are across from each other. So again, you can see that this will be a cis next to or trans across from isomer. And then we can have a really fun one if we think of this octahedral species in which you've got 3 waters and 3 chlorines. So triaqua trichlorochromium 3. You can have this structure here in which you can see you've got a pair of chlorines are trans to each other, and the other one obviously has to be cis to those, or where all of them are mutually cis. We don't say trans-cis and cis-cis. What we do is we see how those chlorines are associated in the octahedron. And this one here, where you've got the trans and the cis, they're sort of occupying a meridian. If you think about it just going around in a nice little semicircle there. So those are called meridional or MERS. And then these here, where if I join them up, you can see they define the face of an octahedron. And so those are called FAC for facial. So geometric isomers you can see in 4 coordinate, you can have them in 5 coordinate, you can have them in 6 coordinate. Cis and trans, in which you've got 2 ligands that are the same, and you just say, are they next to each other cis, or are they across from each other trans? And then where for the octahedral you have 3 ligands, you can have them meridionally, in which 2 are trans, 1 is cis, or facial, in which they are all mutually cis. Finally, let's discuss enantiomers. There is a very familiar one to you, a tetrahedral substance here, like this cobalt, in which you have 4 different things around a tetrahedron, just like the organic 4 different things around a tetrahedral carbon. Take the mirror plane of that, make its enantiomer, and these are non-superimposable. If you try to turn this one round, so you have the ammonia and the water superimposing, then what you find is that the chlorine would be coming out the front and the bromine would be going out the back. Non-superimposable. If you go to our S and R assignments, if you're not sure of that, then there's the organic structure 2 module goes into it quite deeply. The least priority here is the nitrogen. So let's think of having the nitrogens at the back. If we therefore look from the bottom here and we count bromine 1, chlorine 2, oxygen 3, we'd be going around clockwise, which means that's the R isomer. And then looking again from the bottom here, we go bromine, chlorine, oxygen, anti-clockwise. So that is the S isomer. Now, as well as enantiomer in the 4 coordinate, you can get it for octahedra. Obviously, you can have it if all 6 things on the octahedron are different, all 6 ligands are different, but you can also get it because of the constraints imposed by bidentate ligands. So I'm not going to dwell on this because it would need sitting there with huge big molecules. But if you look at this particular compound, chromium with 3 N's on it, where N is of course that ethylene diamine, or the 1,2 ethane diamine. Ethylene diamine, so much easier to say. Well, you can have those coordinated so that they arrange in 2 different shapes. Now, if you think of these look as little propellers here. Okay, now if you take this propeller here, or a little sort of screw or whatever, and this one here, I hope you can see that they are mirror images or enantiomers of each other because they are non-superimposable. And instead of just calling these R and S or L and D, as the biochemists would do, we call them delta and lambda. That's a capital lambda, by the way, based upon how they would rotate if you treated them as screws. I'm not going to go into this, but I hope you can see that if we were to rotate this one clockwise, it will screw into the fluorine that was on it. This one here, to get that screw in, we'd have to translate it anti-clockwise. Very hard to see. I'm not going to dwell on those. We might play a little bit in the live session for that, but otherwise just be aware that you can have enantiomeric coordination compounds. You can have them in the usual expected tetrahedral type structures. You can also get them in octahedral structures in which you have bidentate ligands. So there we are, a little series on the structures of coordination compounds.